Okay, thank you for inviting me to speak. So I'm Benjamin Sach from the University of Bristol. This talk is joint work with Raphael Clifford, who's over there, who gave a tutorial on streaming lower bounds earlier this week, and Marcus Gelsenius, who's not in the room. So the talk is going to be about streaming cell probe lower bounds. So this talk has some overlap in some of the content with what Raphael said, but so the first, maybe third, will have an overlap. I'll reintroduce the information transfer method from scratch, and then we will talk about the Hamming distance problem, which Raphael briefly mentioned, if you have good memories and you can remember as far back as Wednesday. So I'm just going to, that's the last I'm going to mention of that. I'm just going to start completely from scratch. Okay, so this is about the online Hamming distance problem. So what you have is you have a stream of symbols and a fixed string f of some length n. What happens is you have to compute the Hamming distance between the fixed string and the stream of symbols. So here the Hamming distance is 5. What happens is the Hamming distance here is 5. Then another symbol arrives, so the Hamming distance is the number of mismatches. So here, A is different from B, D is different from A, B is different from C, D is different from B, and C is different from D. So there's 5 differences. So this is the Hamming distance. Then a new character arrives. That gives you a new Hamming distance. So the Hamming distance now is 9. That's what you have to output. And then a new character arrives. Hamming distance here is 3. And so on and so forth, and 9. So what we're interested in is every time a new symbol arrives, you have to put the latest Hamming distance, the Hamming distance between f and the last n symbols of the stream. Okay, so yes, just the number of mismatches. And what we're going to show, we're going to discuss, is an amortized, randomized lower bound on the number of cell probes that you have to perform when a new symbol arrives. So this is the number of locations in memory that you have to look at when a new symbol arrives to successfully answer this problem. So any algorithm, even if it's an amortized algorithm, any randomized Las Vegas algorithm must probe at least this many cells, where delta is the number of bits in a symbol that arrives, and W is the word size. Okay, so I'm going to talk a bit about this result and how we proved it. I'm going to start by recapping the cell probe model. So the first thing to say about this is any cell probe lower bound also gives you a time complexity lower bound in the RAM model. So if you prefer to think of it as a RAM model, normal time complexity lower bound, you can think of it like that. The second thing to say is this is an improvement of a previous result we had. So that gets worryingly close to the bottom there. Okay, so in this talk, for simplicity, we're going to assume that W, the word size of the computer, is log n. This is the sort of natural assumption that's most commonly made in theory. So this, in that case, then simplifies to this. So I'm only actually going to talk about this result because it's simpler, but you can actually do this. You can handle all different sizes of words. Okay, so I'm going to talk about this thing here. So if you think of the number of bits that arrive as filling a word in the computer, every time a full word of bits arrives, then this simplifies to log n cell probes. So you have to look at log n distinct places in you have to probe at least log n cells every single time a new symbol arrives, if you have any hope of answering this question. So that's the problem, which was briefly discussed in a previous talk. Okay, so for clarity, let's rediscuss the model, just in case anyone hasn't seen a cell probe model talk this week. So in the model, there's a CPU that has no memory at all. Computation is completely free. The only thing we charge you for is looking at cells in the memory. So there are an infinite number of cells. Each cell holds W bits. This is what's called the word size. And each probe either reads a cell or writes to a cell. So your algorithm can read to any cells it likes, write to any cells it writes, and all I charge you for is looking at particular cells. So some symbol arrives, you look at some cells, I count how many different cells you look at, that's all you're charged. So lower bounds in this model are very hard to avoid because most sane models fit this thing. So in particular, the RAM model, any RAM model lower bound, any lower bound for this immediately gives you a RAM model lower bound, because this is like the RAM model where you have free computation. Okay, so as I said, we're going to lower bound the number of cell probes performed when each new stream symbol arrives. Okay, model clear? Any questions about the model? No? Okay, everyone happy? Seems likely. Okay, so as I said, a cell probe lower bound gives an equal RAM model time complexity lower bound. Okay, and as is relatively standard, and you've seen before, we are going to employ Yau's minimax principle. So a lower bound on the expected running time for, so what we're going to prove is a lower bound on the expected running time for any deterministic algorithm running on a random input. By Yau's minimax principle, this will imply that the same lower bound holds for a randomized algorithm on its own worst input. So we're going to say, we're going to define an input distribution, show that for that random input distribution, any deterministic algorithm has some lower bound. This will immediately apply by Yau's minimax principle that if you took any randomized algorithm, it would have at least that time complexity on its own cell probe complexity on its own worst input. Okay. So here is the overall approach in more cell probey words. So we're going to pick some fixed array f and some distribution over the stream. We're then going to give a lower bound on the expected number of cell probes performed by any deterministic algorithm when it computes the Hamming distances between f and this stream. So it's going to be expected over the distribution, and then by hitting it with Yau's minimax principle, we get a randomized lower bound for any algorithm on its own worst input. Okay. So to do this, we're going to apply the information transfer technique. So what you should imagine is a balanced binary tree built over the stream. So this is the stream. I've built some this balanced binary tree over the stream. If the stream is longer, of course, it would generalize in the natural way. And I can use this to define this concept of information transfer, which was introduced by Petrascu and Domain in a really seminal paper that's been mentioned like 5 times this week at least. So we're going to associate each node with 2 intervals. So here's some node. The interval that it's associated with are the leaves in the left and right subtrees of this node. So, so this is the left interval, this is the right interval. You just take down the side, everything down the left-hand side is in the left interval, everything down the right-hand sides in the right interval. For this node, you can see this is the left interval, this is the right interval, and so on and so forth. So the information transfer associated with some node is just, it's the set of cells that are written to during this period and then next read during this period. So you take all the cells that are written to in here and then next read in here. This gives you a set of cells that the algorithm, this gives you a set of cells, but you should really think of it as a set of probes in some sense. So what I'm saying is I've associated these cells, but these are really, they are reads. They're reads that the algorithm did while processing this stuff that were previously written to in this stuff. So if I tell you that the information transfer of this node is 46, then what I'm telling you is I found 46 probes that the algorithm performs. So I'm telling you that there are at least 46 probes that occurred in here that read stuff that was in here. So if I can tell you the information transfer is large, I can tell you that the number of probes done is large, which is what we're aiming for. So the important thing about this technique is that if I take the information transfer of some node like this, and then I look at the information transfer of, say, this node, these 2 information transfers are disjoint. I'm counting different probes. So the probes that I count in here are, the probes I count in this information transfer are different probes from the probes being counted in here. Between 2 levels, you can see this because this read, this section here is disjoint from this section here. So the reads done in here are disjoint from these reads here. So this does not double count any probes. So again, the information transfer on a particular level, if you go across, because these things don't intersect, there's no double counting in here at all, So you can add all of the information transfers of all of the nodes together to get a lower bound on the number of cell probes. So the number of cell probes being performed by the algorithm is at least this sum here. It's the sum of the information transfers of every node. So where the information transfer, as I said before, is just the cells that are written to during here and then next read in here. Okay. So this gives you the notion of information transfer. So the goal is entirely in the technique to prove lower bounds on the information transfer associated with nodes. So I want to prove that lots and lots and lots of nodes have large information transfer. That means that the number of cell probes is going to be large. Okay, so to achieve this, we're going to link the information transfer to the entropy associated with some particular outputs. So if you consider some node in the information transfer tree, so I've just drawn part of the tree here. If you consider some node in the information transfer, I've now reintroduced the fixed string f. So there's some fixed string f, there's some distribution over the stream. If you imagine taking this distribution and then fixing arbitrarily all of these things in the stream and all of these things in the stream. These things are now random and unknown according to the original distribution. So what I can do is I can think about, and we do think about, the conditional entropy of these outputs. So these inputs are fixed, but during this period, I produce some outputs. The outputs that I produce, hopefully, depend in some non-trivial way on these inputs in here. So what I can argue is I can argue about the amount of entropy in these outputs conditioned on all of this stuff being fixed. So what you can do is you can link this conditional entropy to the size of the information transfer as follows. So what you can do is you can write down an encoding of these outputs using the information transfer. The encoding is, forget the W, it's essentially just for each thing in the information transfer, I write down its address, that's W bits, and its contents, that's W bits. So I've written down 2W times the expected information transfer, it's all conditioned on this stuff, and that's what I've written down as my encoding. Why is this an encoding? It's an encoding because I can now recover, it's an encoding because I can recover these outputs from just this and the green stuff I already know. What do? I run the algorithm up to this point here. I then jump completely over this point and then continue running the algorithm. So now when I'm running this algorithm and producing these outputs, sometimes when I need to probe cells, I need to know whether or not they were cells I wrote to in here or cells I wrote to over here. Fortunately, this is exactly what was encoded in this encoding. That's exactly the definition of the information transfer. So if I need a cell from back here, I can look up whether it exists in the information transfer. If it does, I've got its contents. If it doesn't, then I know it's the same value as whatever value I wrote for it back in the past. So this allows me to spit out all of these answers using only the stuff that's fixed and the stuff I wrote down. So this gives an encoding of these answers, which means it's an upper bound on the entropy, which was given as follows. So we've linked the entropy of the answers to the information transfer. So now if we give lower bounds on this conditional entropy, we have given lower bounds on the information transfer. Okay. So that's going to be the game. We're going to produce lower bounds on this by producing lower bounds on this. So the real game that I'm going to spend most of the time focusing on is how to produce high entropy nodes for the particular problem. So a high entropy node is a node such that for all choices of the fixed stuff, this conditional entropy is large. How large? Basically as large as it could possibly be. So it's as large as delta, the number of bits per word, times delta, number of bits per word, times the length of the interval. So I want to say that the entropy of this stuff, these outputs, even conditioned on all of this stuff, is this, which is up to constant factors the number of bits that actually occurred in here. It's as big as it can possibly be. That's the goal. So if I can show for the Hamming distance problem that for lots and lots of the nodes this entropy is large, then I can use this to prove that the information transfer is large, which I can then use to, which then directly implies that the number of cell probes is large. Okay, so this is essentially what I just said. So why are high entropy nodes good? If you consider some high entropy node in the information transfer tree, by combining the lower bound from it being a high entropy node and the upper bound that we saw before, the connection between information transfer and entropy, if you combine these two things and then take expectation over the choices of the fixed stuff, you get this. The expected information transfer is at least delta times the length. This is missing an LV. LV is this, the length of the interval divided by W. You rearrange, plug it in, you get that. So if I told you that for the Hamming distance problem, all nodes actually have high entropy, then the expected number of cell probes is at least this thing here, which is this. There's a missing omega there, which is at least omega delta over W n log n. So if I can tell you that all nodes have high entropy, then I have that the total number of cell probes over the entire stream is delta over W n log n. So on average, amortized, it's delta over W log n, which is exactly what I wanted. So the entire focus of the rest of the entire talk is to be this, which is to prove that for the Hamming distance problem, for dull technical reasons, only in the top half of the tree, the nodes are going to have high entropy. The reason it's just the top half of the tree is essentially comes down to rounding errors. In the lower half of the tree, there's not going to be enough space in the intervals to actually encode everything we need, all the setup we need to prove the argument. But it doesn't matter, because up here, these are the sort of heavy nodes. They have biggest intervals. So even if you just sum over all of these things, you're still going to get that the expected number of cell probes is at least this. Nodes in the top half of the tree, these nodes are the big ones, so you're still going to end up with delta over W n log n cell probes in total, which is again annoyingly missing an omega. Sorry about that. Okay, so that's the game we're going to play. The game we're going to play is to try to prove that for the Hamming distance problem, at least in the top half of the tree, you can get high entropy nodes. You're going to find some distribution on the stream, some fixed strings such that the entropy is high of these outputs. Okay, so let's have a first attempt at a hard distance distribution. So we're going to try to come up with a fixed string and some kind of stream that produces a lot of entropy in the outputs. So yeah, we need to pick an f and a distribution on the stream so that for any sufficiently large interval, the entropy of these outputs conditioned on this thing, regardless of how I fix these things, is delta, the number of bits in each input string, input symbol times the length of this thing. Okay, so because it looks easiest, and it is, let's start with delta equals 1. So now the stream is only going to contain zeros and ones. The stream just contains zeros and ones. Okay, so you may remember this from a previous talk. This is in fact the hard distribution with a slight modification from the convolution problem. What I'm going to do is I'm going to put ones at powers of 2 positions, and these stars, there are no star symbols in the stream, so they will always mismatch stars at these positions. And remember that the stream is going to contain only zeros and ones. Okay, so I've got some interval here, and what I want to prove is that there's a lot of entropy in these outputs. So if I slide this thing along, nothing interesting happens. I can't work anything out now. Now, here in this region, there is 1, 1 in here. These are stars, these are stars. So this mismatches, this mismatches, this mismatches. All of this stuff, I know this stuff, I know that. I know all of this stuff, I know all of that. So I can subtract off all of those mismatches and directly recover this. It's a 0. I know it's a 0 because I can subtract all of this stuff, I can subtract all of this stuff. These definitely mismatch, so I can subtract these mismatches. So this is a 0. Now if I slide by 1 position, I can do the same game again because there's nothing else unknown that doesn't line up with a star. So this, I can tell you, is a 1. So using this, what I've done is, for the second half of here, I've recovered 1 bit. Every output recovers 1 bit exactly of the input. So if I pick each of these symbols from 0 and 1 independently and uniformly at random, then I can recover omega LV bits of entropy from here. So that implies that the entropy of these outputs is at least LV. For delta equals 1, that's exactly what we wanted. So the natural question is now, what should I do? What should I do? Oh, hang on. OK, you might have said, well, this is a trick of the light. It has to work for, I want this to work for any LV, right? Maybe I just tricked you and set up the right one. Well, actually, as you'll see, if you pick any power of 2 length LV, and they are all power of 2 length because it's a binary tree, if I pick any power of 2 length, it works again. It just works with a different one. So if I slide this thing along, now I get to the point where this one is the only one in this region. These are all going to mismatch. I can subtract the other contributions. I get 0, 0, 1, 0. OK, I get everything back. I get half of the interval back. So for any interval length that's a power of 2, I always get half of the thing back. So this entropy is at least this, for delta equals 1. OK, so the problem is, if I just play this game and I don't change anything, when I increase delta, I only get 1 bit of information per output. For every output, I just get match. If I make this the numbers 1, 2, 3, 4, 5, I just get whether it's a 1 or not a 1. I get a match or a no match. That's only 1 bit. So increasing delta hasn't helped me in any sense here. This might look sort of like the wrong approach. OK, so we're actually now going to see a sort of high-level view of our hard distribution. So the higher-level view is like this. Take the original distribution, and to cope with larger delta, I'm going to replace each of the ones not with a single character, but with some substring called p, which I'll define in a minute. So this p is going to have length polynomial in 2 to the delta. 2 to the delta is like the number of different symbols in the stream. So it's going to have some length that depends on the number of different symbols in the streams. We polynomial in that, and I'm going to replace each one with that. So the scale has now just gone wibbly in some sense. This is now a substring of some length polynomial to 2 to the delta. There's another copy of p here. There's another copy of p here, and p there. So it's now 2p, 4p, 8p, 16p. And these stars are now actually repeats of p stars in a row. So I've just blown the thing up by a factor of p. So now what happens is that instead of having single characters in the stream, I'm going to divide the stream into blocks. These blocks have twice the length of this p thing here, and they are going to be drawn independently and uniformly from some big set that I haven't yet specified. There's a big set of size p to the power of theta p of lots of different options for these blocks. And so what I'm going to do is, OK, so now as before, there are lots of p's in here. I can't tell anything. But if I slide on a bit, I now get to the point, aha, now these are all going to mismatch. This stuff I know, so I can subtract it. This stuff I know, so I subtract it. So the only thing going on in here is, by taking everything off, what I find out is, as I slide along by 1, 1, 1, I'm sliding along by 1, I'm recovering the Hamming distances between this and this block here. So as I slide through this thing, I get all of the Hamming distances between this block and this thing here. And I'm going to tell you that because of the way we're going to pick p and the set of blocks, in fact, we will prove that sliding this specially chosen p over any of these blocks from this set recovers entirely its contents. So now, instead of having a single character that's recovered by a single character, I have a substring p that recovers a substring of the text. So that's the game, essentially. And this is, in some sense, the tricky bit to prove. So now I've just glued things together using the old technique. So just to imagine, this is true. Sliding p over any of these blocks recovers its contents. It's pretty easy to stitch things together to get the result. So any interval of length LV contains, this is just the wonder of division, LV over p of these blocks. We recover p delta bits from each block. This is because there are p to the power of theta p distinct blocks. And what I said earlier was equivalent to saying delta is log of the size of p. That we will prove in a bit. So it's delta is log of the size of p. You get one of these things uniformly at random. So you get this many bits back from working out exactly what this thing is. You've got this many blocks. So if you times these things together, you get delta times LV. So if we can work out how to pick these blocks and this p in such a way that you get this. So this is what we need to do. We want to prove that for any q, there exists a p of length q and a set. So this length q is a set of q to the theta q distinct 2q length ones of these, such that sliding p over this recovers exactly and uniquely and entirely its contents. Big set of possible blocks that can all be recovered by sliding them over p. OK, I'm now going to rephrase this thing to make it a little tidier. It's not going to make much difference. So here's the definition. The Hamming array is just the array containing all the distances between p and every substring of some block. So I take my p, take my block, I slide it across, I write down all of those Hamming distances. That's called the Hamming array. So what we're actually going to prove is that for any q, there's some pattern, some p of length q, such that sliding p over every possible one of these, so take every 2q length string over this alphabet q, slide p over every single one of these things, and then work out how many different Hamming arrays you get. So I claim that if you pick p right, there's going to be q to the power of theta q distinct Hamming arrays if you try q against every single possible thing. So to get from this to this, you just sample for each Hamming array, you take a block that makes that Hamming array. So you just take, for each Hamming array, you take one of these that has the Hamming array. Now they're all distinct, and the set is this size, at least, because you just take one for each distinct one. OK, so we can get from here to here. So the rest of the talk will focus on actually proving this thing, which says that there's some special p such that sliding it over every possible thing generates a lot of different arrays. So in some sense, all I've really achieved in the last, 25 minutes is to get from an online problem to something that looks quite similar in an offline setting. I have some pattern. I want to specially pick a pattern that you slide over stuff to generate lots of different arrays. This looks very similar to the original entropy question. But crucially, it's now sort of offline in some sense, and it doesn't have lots of different intervals to fiddle around with. So it's tidier and easier to play with. OK, so on our way to generating this, I'm going to have to tell you something that initially looks unrelated. So this is you'll see why this is a lie in a minute. But so V is going to be a set containing mu squared binary vectors. Each vector has length mu. So I imagine some set mu squared binary vectors, each of length mu. What I want you to do is pick any mu vectors from V. I've picked these ones. These are the ones I've picked. I take them and I compute their component-wise vector sum. So I write them out as vectors, and like that, just drag them all out. And then I sum these things up. Good. 5, 2, 1, 2, 3, 2. There's no mods going on in here. There's no carrying. I've just added the components up. So the question is, how many different sums can you get? How many different ones of these can you get if I play this game, choose any mu vectors from V? Obviously, that depends on V. Certainly, well, not certainly, there exists a V so that there are mu to the power of mu distinct possible sums. So actually, this is, as we'll see in a minute, a cheat. It's a slight simplification of what we need. This is relatively easy to prove. Just pick them at random, and they're pretty likely to have this property. Here's a boring technical qualification. V is actually a multi-set under the definition that we need. It doesn't make any difference. Just ignore that I said that. But it's technically might be a multi-set. But don't worry about that. It doesn't really make any difference. OK, so this thing here has some similarities in some sense. I can pick lots of different possibilities, add them up, and get lots of different sums. So these sums in some sense look a bit like Hamming arrays. I have the advantage that these things, I'm picking them independently from each other. They don't overlap in any annoying ways like Hamming distances do. OK. So what I want to do is I want to use this to prove this thing that we saw a minute ago. So what I'm going to do is, here's the idea. We're going to take these vectors, and and the vectors are going to be embedded very literally in the pattern. The pattern is essentially just going to contain the vectors in some encoded form. So I'm going to take the vectors, the mu squared vectors from V, each has length mu, and I'm going to put them in P. Literally one after the other, pretty much. And then what I'm going to do is I'm going to repeatedly encode subsets of V. So I'm going to pick mu vectors from V, and I'm going to encode them in this block. So in such a way that the different vector sums are going to lead to different Hamming arrays. So because I've got lots of different vector sums, this will allow me to produce, I'm going to literally tell you how to construct blocks. This will allow me to produce lots of different blocks with lots of different Hamming arrays, because I have lots of different sums. This is essentially the game. Okay, so let me tell you how to construct this P. So we're going to take the vectors from V. Essentially just look at the picture. We're going to take the vectors from V and put them in P as follows. So I'm going to take each vector, and that corresponds to, and this is length mu. This is a mu length substring of the pattern. There's one for each vector. And what I do is I just put it in literally, except that I replace all of the zeros with stars, which won't occur in the stream. They are going to mismatch. And I place the ones with the index of the substring. So here, 1 is replaced with 1. Here, 1 is replaced with 2. Here, 1 is replaced with 3, with 4, with 5, with 6, with 7, with 8. And so on and so forth, 9, with 10, with 11, with 12, and so on and so forth. So every substring has like a special identifying symbol for the ones and a guaranteed to mismatch symbol for the zeros. Okay, so I've literally, in a very physical sense, embedded these vectors within the pattern. I'm going to do this in such a way that allows me to, I've done this in such a way that's going to allow me to embed different possible sums in the stream. Okay, so this is now a process for constructing a lot of different possibilities for blocks. So this is the pattern, this is the stream, and I'm going to tell you how to make a lot of possibilities. So it's going to start with all diamonds. Start with all diamonds in this block. These diamonds aren't going to occur in the pattern, so they're going to mismatch absolutely everywhere. Then I'm going to pick mu vectors from V and identify the corresponding substrings in P. So from V, I've picked this one, and this one. So the corresponding substrings are this substring, and this substring. And to mark that I've picked them, I'm going to replace the character directly after with the appropriate symbol. So I've picked this, so I put a 1 here. I've picked this, so I put a 3 here. I've picked this, so I put a 6 here. I do that for every single thing that I've picked and only for the things that I've picked. Now, consider the next mu Hamming distance outputs. So what I get here is I get 1 match, 3 matches, 2 matches, no matches, 2 matches. Fingers crossed. Now, I claim the matches correspond exactly to the sum of the chosen vectors from V. If it's wrong, it's just because I wrote it down wrong. So take the vectors back up, work out the sum, 2, 0, 2, 3, 1. They actually come out backwards. So whatever sum I pick, whatever vectors I pick, their vector sum is exactly, in reverse, the Hamming distances that I receive from the next mu distances. So because I have a huge number of choices of different vectors, I can make a huge number of different Hamming distances. And everything else is always going to mismatch because the way the construction works. So we can produce lots of different Hamming arrays. I mean, the next mu output part of the Hamming array has lots of different possibilities. Okay. So notice that because delta is log of mu, because mu is like the cube root of q, this is like delta bits per output. Of course, I have to be able to repeat this argument lots and lots and lots of times, and fortunately, you can. So what we're going to do is I'm going to try to repeat playing this game. Now I'm going to pick another mu vectors from V and identify the corresponding substrings. So I've now picked these 3 vectors from V here. I take the symbols directly after, and I insert a 1 to indicate this, a 4 to indicate this, a 7 to indicate this, and now, exactly the same way, the next mu Hamming distances will give the sum of the chosen vectors. And there are mu to the mu different possible sums. So I sliding by mu, that gives me the next mu Hamming distances. And I had a huge number of possible choices for what they could be. OK, sanity check. Which vectors can we actually pick next? I actually can't pick any of these vectors because these vectors are blocked because these spaces are already filled. If I now change these things, I'd change the previous Hamming distances. I can't do that. It mucks up the argument. It doesn't make any sense. So actually, what I've said so far doesn't work because some of the vectors get blocked. Every time you fill some stuff in, you're essentially blocking some vectors that you could have picked. So yeah, each round, each time you do this game, you block mu of the mu squared vectors. So this is the actual vector lemma, which is slightly harder to prove and uses some cyclic coding theory stuff. I thought about presenting that too. I haven't got time, and even if I did, I think what I'm about to show you looks about as plausible as the original thing, so I'm not quite sure what the point would be. OK, so now instead, to allow for the fact that some of these vectors might be blocked, instead of having, so we can still have mu squared binary vectors, each of length mu, but I'm now going to let v prime be an arbitrary subset. It's like 63/64 of v. It's pretty big. Most of v, nearly all of it. And now, instead of choosing from v, I force you to choose from v prime. So you choose these things from v prime, you take their vector sum, and I ask you the same question. How many different vector sums can you get? So what we prove in the paper is there exists a v such that every v prime, there are still mu to the power of mu distinct sums. So even if I remove some of the vectors adversarially, you're still in good shape. So you pick the v, some adversary removes some vectors, you'll still have lots of different combinations available. So the fact, yeah, it's still a multiset. So the fact that some of these things are blocked doesn't make any difference, except that I have to pick unblocked vectors. So I just can't pick things that are in blocked positions that already have things in front of them. But that's OK, because I'm only removing mu things every round. So in fact, what I can do is I can still perform mu over 64 rounds of this before too many things get blocked. OK. Yeah, if you do this many times, you've now blocked as many vectors, and we're in trouble. OK, so if you work this out, you'd realize I haven't actually filled out, I've only filled out like mu squared over 64 of things in here. It's nowhere near enough things. There's like mu cubed things in here. So I have to fill out more stuff. So to free everything up, after mu over 64 rounds, we shift along by one character. Shift by one character, that now unblocks every vector. Because previously, every index we modified had I mod mu equals 0. Now we're working with I mod mu equals 1, so I can play the entire game again. Everything's unblocked. I can start with another mu over 64 rounds. Then everything gets too blocked up again. So then I can do another shift, and now working with the stuff I mod mu equals 2, and so on and so forth. So I do a total of mu squared over 64 rounds with a single shift character every mu over 64 rounds. So, yeah. So this is actually the full construction of both P and the blocks. So what I've done is OK, so what have we achieved? So this construction of a block gives you mu to the power of theta mu distinct options for every, it's not quite every, let's go for every stretch of mu contiguous Hamming distances. I get mu to the mu different options of all of the possible set of outputs for length mu. The length of this thing is 2q. I just remember that from before, which is equal to 2 mu cubed. So there are at least this many possible things. So for each mu length stretch, I get to pick the options for its Hamming distances from a set of this size. So I get, if I simplify these things and work out what the value of q ever was, I get q to the q possible distinct one of these, each with a distinct Hamming array. So the Hamming arrays are all distinct among all of these things. So therefore, we've literally proven this thing here, except I left out the proof of that vector thing because we don't have time to do it. Okay, well, I don't. I could speak faster if you like, but probably no one wants that. Okay, right, so, and now, how much time do I have? 10 minutes, great. Maybe we did have time. Okay, so now what I'm going to do is I'm just going to come up for air, as it were. I'm going to work backwards through the stack and plug everything back in so we can see where it came from. So what we've proven is that for any q, there is some pattern of length q such that if you slide this thing over all 2 q-length blocks, I get a huge number, q to the q, distinct Hamming arrays. So this implies what I said I actually wanted, which is to prove that for any q, there exists a pattern P of length q and a set of distinct ones of these, such that sliding P over any one of these uniquely recovers its contents. So you get the entirety of the contents of this back from sliding this over here and looking at its Hamming distance array. So I can do this by just taking each one. I just do this by looking at each Hamming array and taking a unique one of these for each Hamming array. That immediately gives you this. So now we have this. If you just take this and delete some stuff to make it shorter, what we actually wanted was we slide this P over any one of these things and it recovers its contents entirely. We want that because if you go a level up, we want this because we have an unknown stream where this stuff is fixed and this stuff is unknown. We've inserted P power of 2 positions, and we have, because we can slide this over any one of these and recovers its contents, we can recover P delta bits from each of these blocks in the second half for each of the LV over P blocks, because there are P to the P distinct blocks, and delta is log P. So we have that if we multiply these things together, we get that the entropy of these outputs, conditioned on all this stuff being fixed, is indeed delta LV. So this is indeed a high entropy node. So these are high entropy. So we have that this is a high entropy node. So all of these things is high entropy nodes. I didn't really mention the top half thing, but really it just comes from rounding errors I hid in the talk. So each of these things is indeed a high entropy node, which implies by the original inequalities that the number of cell probes is at least the sum of, so the number of cell probes is the sum of the expected information transfer. We just proved that these things were delta LV. If you sum over all these things in the top half, you get exactly this. Okay. Yeah, so that's the thing, as it were. So, right, so what we've proven is that if you want to compute the Hamming distance in a stream, you have to do at least delta over W log n cell probes every time a delta bit symbol arrives. Actually, by improving the encoding argument, nothing to do with the distribution, nothing to do with the stuff that don't change the distribution at all, just change the encoding argument, you can improve this lower bound to delta log n over W plus log n, and now you are permitted to choose whatever word size you like from 1 up to theta log n. Okay, so I think maybe unless I will just end by telling you some open problems. There are a fair few open problems in this area, the sort of stringy, streamy kind of things that you might want to think about instead of Hamming distance. So the game is take exactly the same setup, but instead of talking about Hamming distance, replace Hamming distance with some other natural distance measure that people care about. So, for example, so here are some things that seem hard that we've thought about and we don't know how to make progress with. Edit distance or longest common subsequence. These are hard with non-binary alphabets because consecutive outputs differ by at most a constant. This means that the entropy per output is constant regardless of what distribution you pick, which means that none of this stuff involving entropy is going to work. And there are, I would argue, pretty good reasons that I won't go into why the other techniques you've seen for cell probe lower bounds don't seem likely to work either. So this is an interesting question that looks like it's going to require new techniques. This is particularly tempting. It's a problem for the existing techniques because it's a decision problem, so yes or no answers. So you just want to do exact pattern matching with wildcards, cards that are symbols that are allowed to match anything. This is a decision problem, so the entropy per output is constant, which rules out the existing methods we know how to apply it to. But it's nice, one, because it's a sort of natural sounding problem, but two, because the existing upper bound for it is log squared n online per character, or log n log n offline, so a log n lower bound here, which looks quite plausible, would be pretty close. Another natural question is approximating the Hamming distance. So instead of giving the exact Hamming distance every output, I just want you to give it within a factor of 2. This also is mean to the methods because the output sort of can contain rounded answers. I could just always output a power of 2, for example, and then the entropy would be like log instead of log. That would be bad. This L infinity distance, maybe I'll just tell you. So L infinity distance, you want to find the largest absolute difference between anything in the fixed thing with anything in the vector. So line them up, find the largest absolute difference. This is very tempting because there's no obvious reason why you can't prove a lower bound for this, other than the fact that it doesn't fit in our setup for the it's almost overlooked point that in the Hamming distance problem you could subtract off all of the mismatches from the stuff outside the window that was fixed. But for L infinity distance, you can't subtract anything off. It's not what we would call local. From the total answer, you can't work out anything about the internal structure of the answer. So this, there doesn't seem any really obvious reason why you can't prove a lower bound for this, but it's kind of tempting to want to, partly because upper bounds, no one knows anything better than the naive order n solution of looking through the entire thing and working it out for the actual problem of L infinity distance, as far as I'm aware. Maybe, I'm pretty sure about that, but I could be mistaken. Okay, so that's not a good reason it doesn't fit in our setup, but I don't know how to do it. That looks like the easiest one to do. Yeah, anyway. Questions?